Okay, so the trick to doing these first few problems is to just keep in mind how much of the kinetic energy changed. So we want to know what was the initial kinetic energy and what is the final kinetic energy, and the difference between them is going to be due to the work done on the system. So if I look at this first example for number one, my boat started out at 2 meters per second, and now it's going 4. So the point is, it's now going 2 times faster. If you're going 2 times faster, that's going to be 2 squared times, or 4 times as much energy. So the trick to kinetic energy is just remember the kinetic energy equation, and I apologize, I don't have my stylus, I'm doing this with my finger, but it's kinetic energy equals 1/2 mv squared. So since this is a squared relationship, if you double, as you did here, from 2 to 4, then you have to not double the kinetic energy, but it raises it by 2 squared, so 4 times as much. So here we're using 2 bars to represent 2 units worth of kinetic energy. I'll have to have 4 times as much, so that's 8 lines high. So I draw this 8 lines high, representing 4 times as much kinetic energy as what I started with. And the difference between here and here, between my start and end, must be due to the work done on the system. So the idea is energy is conserved. So however much energy I added to the system, which is what work is going to take this plus this to get this. So the difference between here and here is 6. So that's the amount of work done. 2 units of energy plus 6 units of work gives me a total of 8 units of kinetic energy. Now in this next one, we start at 2 in the opposite direction and end up at 4 in that direction. Well, again, basically we're going 2 times as fast as we were to begin with, so the kinetic energy is going to be proportional to 2 squared, which is 4. So it's the same thing. If I start off with 2, I have to end up with 8, and therefore I must have added 6 units of energy to get there. Now our next one, we have a tugboat that starts out going 4 and ends up going 2. So basically it's going 0.5 times as fast, 1/2 as fast. Well, 1/2 squared equals 0.25. It has a quarter as much energy when it's done. So this one starts off with 8 and ends up with 2. So therefore the amount of work done is the difference between there. So to take 8 and reduce it to 2, I must take away or change its energy by 6 units. So I'm still doing 6 units worth of work, but in this case it's negative work because it's taking energy away from the system. So work is the change in the energy of a system, and in this case negative work means I'm subtracting from the energy of it to reduce it. Sorry to be repetitious here, but what we got is this is what we've done before. We're going from 2 to 4. Therefore, I'm going 2 times faster, which I'll have 4 times as much energy. So I start off at 2. I end up 4 times greater than that is 8. And what do you have to add to 2 to get to 8? How much do you have to change to? You have to change it or do work equal to 6 units. Okay, we've been there, done that. Now what's weird though is this next one. This can be a little bit confusing. So at first I had 2 units of energy in this direction and I ended up with 4 meters per second in the other direction. Well, the thing is, energy is a scalar quantity. It doesn't matter what direction you're going. So I can just look at it and say, well, if it was going 2 here and it's going twice as fast, even though it's in the other direction, I'm going twice as fast, the amount of energy is going to be 2 squared, or it's going to be 4. And you can't have negative kinetic energy, so what I have then is I start off with 2, I end up with 8, the total work done is 6, just like it was up here, which seems kind of counterintuitive because here the boat started off the same in both cases. In this case I simply had to make it go faster. In this case I had to slow it down and then make it go this way. So in slowing it down I had to do negative work. I had to get rid of 2 units, which would have brought me down 2. And then I had to push it to get it to 8. So I would have gone down 2 and up 8. So the net change is 6. But the easiest thing to do is to forget about how much work I had to do to slow it down and stop it, as much as you probably want to think about that. And just look at, I started off with 2, I ended up at 4. Its kinetic energy is 4 times greater than it was to begin with. And our next one here. So what I've got is a 100 Newton box that's being pushed this way or pulled this way, and I have friction force going the other way. So let's just see what our coefficients of static and kinetic. So static friction is 0.6. So what I have in this direction here, I have a static friction force of 60, and I just need to use that to check to see if it will accelerate. Since I'm applying 80, it's going to accelerate. You never do work against static friction, because it only applies when the object is not moving. If the object is not moving, you're not doing work. But you do need to make sure that you can, in fact, move the object. And since I can, then I just go to the kinetic friction, and I see that's 0.4. So the actual force of friction I'll be working against in this case is 40 newtons. So let's go ahead and do our bar chart then. I've got energy in 2 forms. I'm doing work against friction, and I'm adding energy and doing positive work on the block. So let's just see what I've got here, but I've got to go to the next slide. So what I have here is the work done by the applied force is going to equal the applied force, which was 8 newtons, times the distance it moved the object, which is 5, which is a total of 400 units of 400 joules of energy, and that's going to be positive work because it's making the object. If the force is acting in the same direction that the object is moving, you're doing positive work. So that's 400 units here. Now, friction is going to be negative work because friction is pointing this way while the object is moving the opposite way. So anytime the force is opposing motion, it's negative work. So what I have is negative 40 times 5 is 200 units of negative work being done. So now the total work done is going to equal this 8 minus this 4, which is a total of 4. 400 joules worth of work were done. Now, it didn't have any kinetic energy to start with. It was starting from rest, so the total kinetic energy is equal to the net work done on the system, 400. But that's not going to be the case for all of these. Let's see what else we've got here. These are classic problems here. So let's see what we have here. I have a 100 Newton box that's moving upwards. So in this case, what that tells me is that my hand is doing positive work because it's applying a force in the same direction as motion. And gravity must be doing negative work because that 100 newtons of force that's acting on the box, the weight of the box, is in a downward direction while the box is moving upwards. Now, the first thing I'm going to do in this problem, however, is I'm going to figure out what the starting kinetic energy of the box was. So I'm told that the box is moving upwards at 10 meters per second. So if it's a 10 Newton box, it has a mass of 10 kilograms. So I have 10 kilograms, 1/2 of 10 times 10 squared. 1/2 of 10 is 5. 5 times 10 squared is 500 joules. So here, for the initial kinetic energy, I'm going to go ahead and put in 500 joules. Now, the next thing I've got to do is I've got to figure out how much work is being done on the system. So let's see how much work is done by gravity. I have 100 newtons, and I moved it an amazing, 5 meters. An amazing 5 meters. So negative 100, because it's going against motion, times 5 meters gives me negative 500 joules worth of work done by gravity. And then the applied force is in the positive direction, in the direction of motion. So I'm going to say 80 newtons times the amazing 5 meters of hand motion gives me positive 400 joules, which I'll put here under applied work. Now when I combine 400 with 500, I get 100 for my total, negative 100, because this was negative 500, so I get negative 100. So if it started off with 500 joules, and I take away 100, then it ends up with 400 joules, which tells me it's slowing down. Without doing this, it could be very confusing, I must admit. Alright, on to number 8. Again, I have a 100 Newton box. Again, it's going to move 5 meters. Again, it's moving upwards, so the applied force is positive and the work done by gravity is negative. So because the initial setup is the same, I know I have 500 joules worth of kinetic energy, which I'll put here under K initial. Then I'm going to go and see how much work is done. So the work is done by gravity and applied. Now gravity, once again, is going to do negative 100 newtons times 5 meters. It's negative because the object is moving up and gravity is pulling down. That gives me negative 500 joules, which I put here on my bar chart. But now the positive work done is 120 times 5. So 120 times 5 is 600 joules of positive work done, which is here. So in this case what happens is, when I find my total, it's going to be 600 minus 500 is positive 100. So in this case, unlike the previous one, I start with 500, I add 100, and I end up with 600. In this case here, the box is gaining velocity in the upward direction. Let's say, whoops, let's try to scroll up. Alright, now, in this case, number 9, the box is moving downwards. So we're just going to take the previous example and just change it a little bit here. Since the box is moving downwards, and we've changed the weight of the box, it's an 80 Newton box, we've got to be careful there. So first let's calculate the kinetic energy. If it's 80 newtons, it's an 8 kilogram box, so half of 8 is 4, and 4 times 10 squared is going to be, because it started off, it's got the same initial velocity, it starts off with a kinetic energy of 400 joules. And let's go ahead and see how much work is done here. The amount of work done by gravity, in this case, since the object is moving downwards and gravity is pulling it downwards, in this case, gravitational work is going to be positive. So I have 80 times, again, 5 meters, so 80 times 5 is 400 joules. The applied force is going to be negative, it's going against the motion of it. So this 120 newtons is going to be negative, since it's opposing the motion. So 120 times 5 is negative 600. So let's just see what happens. We should be able to look at it and go, wait a second, if the negative work is more than the positive work, this baby's slowing down. Let's just see. Okay, so let's just go over this again. The object started with 400 joules of kinetic energy. Gravity did 400 joules of positive work on the box, and the applied force, which was opposing motion, did negative 600 joules of work on the object. So to find what the total work is, it's going to be negative 600 plus 400, which gives me negative 200 joules worth of work. So it started off with 400 joules of kinetic. We did negative 200 joules worth of work on it. In other words, we took 200 joules away from it, which leaves us with 200 joules of final. And yes, it's slowed down. It's not twice as slow though. It's 1.4 times slower because, remember, velocity is a squared function. Just saying. Alright, let's see here now. Alright, now we got some spring energy going on. Let's see if I can get it all on here. I think I can. Let me make it. I think that'll work. Okay. So, the 40 Newton box pulled a distance of 4 meters on a rough surface, constant force of 100 newtons. Whoops, that's not what you want. We have kinetic friction is 25 newtons. Here's our spring constant. So we want to do a bar chart when the box is pulled 4 meters. Okay, so let's just see what we've got here. Let's see. First of all, I know the kinetic energy to start with, the initial kinetic energy is 0. So that makes my job a little bit easier here, a lot easier here. So let's start off and see how much work was done by the spring. Spring is always negative work. It always works against you. Alright, so if I pull it this way, the spring obviously pulls the other way. So in this case, to find the work done by the spring is going to equal, right here, we're going to say the work done by the spring equals 1/2 kx squared. K, the spring constant, is 6, so half of that is 3. The distance it was moved was 4 meters, so that's 16. 16 times 3 is 48 joules. So I'm going to draw that here. It's pretty close to 50, so we'll go 48, and that's negative work because it always opposes my motion. Springs are always going to do negative work. Now, let's see. Let's try doing friction. So since it's a 40 Newton box, that means I have a 40 Newton normal force. 40 times, what's my coefficient of friction? Oh, I was just told the frictional force. The frictional force is 25. That makes it a lot easier. So the work done by friction is going to be 25 times 4, and that is 100 joules worth of friction. And friction is going to be like spring force, always opposing motion. It's always going to be negative. So here I have 100 units of negative work done by the friction. And then the applied force is 4 meters times the 100 newtons of force that's pulling on it. So that gives me 400 joules worth of applied force. So that I have 400, negative 100, and negative 50. When you combine those, what you get is 250 units of positive work, so therefore 250 units of kinetic energy. Okay, now I just got the box going the other way. Now, in this case, I'm told what the mass of the box is. It's an 8 kilogram box that is going 10 meters per second. So it has some kinetic energy to start with. So I'm going to calculate its kinetic energy. K equals 1/2 mv squared. 1/2 of 8 is 4. 10 squared is 100. So I have 400 joules of kinetic energy to start with, which I'll put right here under kinetic initial. Now I've got to figure out what the total work done on it. So I've got work being done in this case by the spring and work being done by friction, both of which are going to do negative work because they're opposing motion. So let's just start off with the amount of frictional force. The frictional force is going to be friction force equals mu times normal force. The normal force is going to be mg, that's 80. So I have 80 times the coefficient of kinetic friction, which is 0.625. That gives me 50 newtons of friction force. So I'll say, well, if I have 50 newtons acting across a distance of 2 meters, that gives me 100 joules of negative work being done by friction, which is right here. And then I've got the spring. Now the spring is going to be 1/2 kx squared, and so the spring constant is 100. So half of 100 is 50, and the distance is 2. 2 squared is 4. 50 times 4 is 200 joules of negative work being done by the spring. So the total amount of work done is negative 200 and negative 100. That's negative 300. So here's my negative 300 joules worth of work. So I start off with 400 joules of kinetic, take away 300 joules through the work done by the spring and friction, leaves me with a net of 100 joules that are remaining.